Hello, my name is Charles Cassette, and today I will be presenting our work on the relative position estimation between two ultra-wideband devices with IMUs. So first thing I'm going to do is describe the exact problem scenario. So suppose we're in a situation where we have two robots. They could be quadcopters or generic sensing devices even. And aboard each robot, we have an IMU as well as an ultra-wideband transceiver. The IMU has an accelerometer, which effectively measures the agent's acceleration, a gyroscope, which measures the angular velocity, and a magnetometer, which measures the local magnetic field strength. The ultra-wideband transceivers are capable of measuring the distance to the other transceiver aboard the other agent. So the problem is, with these sensors, how can we estimate a full 3D relative position of the blue agent relative to the red agent? So why do we care about this problem? Well, for one, it doesn't require GPS, so it could be a solution to robot navigation in GPS-denied environments. Also, it could be a good solution for relative positioning in multi-robot teams. And many of the reasons why we're attracted to ultra-wideband specifically is because it's cheap, it's lightweight, small, it runs on low power, it provides roughly 10 centimeter accurate distance measurements, and it can also be used for inter-agent data communication, where this last point provides this pretty elegant two-in-one solution for multi-robot missions. So the presentation structure is going to be as follows. It's going to be divided into two parts. The first part is going to be very conceptual and mathless, and we'll talk about the specific challenges as well as the concept of our proposed algorithm. The second part is going to go into the details and mathematics, where we will describe our algorithm architecture as well as something called the keypoint selection algorithm, which is like a core aspect of our solution. So back to this scenario, describing like the main challenge behind this problem. Suppose we have these two robots again, these cartoon quadrotors, and we've just received a distance measurement between them. Well, some of you may intuitively see that calculating a relative position from this information is difficult because the blue agent could lie anywhere on this circle with radius equal to the distance measurement. And this makes this estimation problem unobservable. The proposed solution, however, is going to exploit the agent's history, its old trajectory, to calculate a 3D relative position. So as the agents move around, they'll be collecting lots of distance measurements at multiple times per second. And it turns out that if your trajectory is exciting enough, i.e. not traveling in straight lines, etc., then this is sufficient information to calculate a 3D relative position of the blue agent relative to the red agent. But we cannot incorporate and fuse an arbitrary large amount of distance measurements in the past. We can't take thousands of distance measurements and fuse them all together to calculate a comprehensive 3D relative position estimate, because that will require too much computation. And on board these agents, we have a limited amount of computational resources. So we're restricted to taking into account a lower finite amount of distance measurement at any one time. So for this illustration, we're going to say that we can only take into account 5 distance measurements at once in a single state estimate calculation. This is going to motivate using something called a sliding window filter, which does exactly this. And as time progresses, the red agent is going to move a bit forwards in time, and then take into consideration the 5 most recent distance measurements, move a bit more, the new 5 most recent distance measurements, and so on and so forth. And what we will show in this presentation is that it's actually beneficial to deliberately take into account older distance measurements than the 5 most recent distance measurements. And So now we must choose which distance measurements in the past that we take into account. And we're going to call these special instances in time in the past keypoints. And so now we have a keypoint selection problem that we must solve. Which distance measurements do we choose? And then one last challenge is that in between these keypoints, we may potentially receive hundreds or thousands of IMU measurements since it's a very high rate sensor. And therefore we use something called pre-integration to relate the state at any two key points by a single equation. And with pre-integration, we can now access distance measurements that are arbitrarily far in the past with minimal, virtually no addition to the computation time of the algorithm. And right away, we'll show the benefits of key point selection. So on the left, we have a visualization of what our algorithm is going to look like, where notice that it's specifically holding on to some distance measurements in the past in the interest of improving performance. And on the right, we have experimental results, where the first column of this table here, or actually the entire table showing the average positioning error over a specific trial, and the first column is the results of our proposed algorithm. And notice how it can be up to 2 to 3 times better than our chosen benchmarks, which is a plain vanilla sliding window filter and an extended Kalman filter. So now, going into details, the algorithm architecture is depicted in this graphic here, where there's two main estimators that are happening in parallel on board each agent. The first one is an attitude and heading reference system, shortened as AHRS. This is an extended Kalman filter, and it computes the agent's attitude relative to some world frame by using all the IMU data. After that, it then computes and outputs a translational acceleration estimate in the world frame of the agent it belongs to. Then the two translational acceleration estimates of each agent are communicated and fed to a relative position estimator, shortened as RPE. And this is a sliding window filter. So the sliding window filter takes the translational acceleration estimates as well as the distance measurements and fuses them to produce a relative position estimate. And we'll note that the separated architecture with attitude states in one estimator and translational states in another estimator, this is called loosely coupled, and we will admit that this is the biggest possible loss of accuracy in our algorithm. Like, the loosely coupled architectures are generally suboptimal, and while we acknowledge this, it does come with certain advantages and simplicities that make this worth it, and we will explain that in a second. So going to a few more details on the relative position estimator, the RPE estimates the relative position and velocity, actually, which is shown in equation 1, where we've stacked the position and velocity into a single state vector. And thanks to our loosely coupled architecture, the relative position dynamics become linear, and those are shown in equation 2, where the input to this system is the difference between the translational acceleration estimates of agent 2 and 1, respectively. And the sliding window filter estimates, so all of this was the this was a state estimate for a single time step. A sliding window filter estimates the state at n time steps, where we stack a bunch of different state estimates into a single large state vector. And at which times we estimate the states, well, that's the same thing as choosing the key points, right? So the key points are identified by this set shown as script k here, which are the time step indices of the states that are being estimated. So now the problem is, how do we choose this set script k here? Which points in time do we include in our large state vector? So the way we choose key points is that we have this what we call a greedy algorithm, where we loop through the agent's history, placing key points one by one at the location that instantaneously minimizes equation 4 the most. And equation 4 is the cost that we choose. So the first term here is something called the square of the geometric dilution of precision. And minimizing this term will cause the key points to kind of like fan out or like be placed like far apart in time. However, if the key points are placed too far apart in time, then you'll have to do excessive IMU integration or pre-integration between two key points, and this can result in a degradation of performance. So that's why we append the second term here, which penalizes the key points for being placed too far apart in time, and it is the sum of the time difference between all the key points. And gamma is just some weighting parameter that balances the two terms. So we tune this by hand, and on the bottom graphic here, if we have gamma equals 0, then we're purely minimizing the first term, the geometric dilution of precision, and this causes the key points to be placed far apart in time. If we have gamma equals 100, then we obtain some sort of balance between the two terms. And if we have gamma be some very large number, then we actually recover the naive or the plain vanilla sliding window filter, which just takes the most recent distance measurements as the key points themselves. Finally, for pre-integration, again thanks to our loosely coupled architecture, giving us linear dynamics, then this makes pre-integration trivial. So two non-adjacent states, xi and xj, can now be related by equation 5 or 6, where we note that aji and bji don't depend on the state. And it can also be shown that bji can be separated into these two terms here, where one of them only depends on measurements from agent 2, and the other one only depends on measurements from agent 1. And this is really convenient because this implies that the agents can pre-integrate their translational acceleration estimates on board and then share that result, as opposed to sharing all the IMU measurements at super high frequency, which would literally be infeasible due to a limited communication capacity. Finally, some simulation results. We have on the left, on the top left, a computation time histogram. And we see that our algorithm is slightly slower compared to the other two benchmarks, being a sliding window filter and an iterated extended Kalman filter. And this slight increase in computation is due to the key point selection step that we do. But this is very much warranted by the increase in performance that we see in the bottom left, where we've run this in simulation 200 times and we see that our proposed algorithm outperforms all the benchmarks that we've chosen. And just a reminder, in the experimental results, where the benefit is even more pronounced, our proposed algorithm has a 2 to 3-fold reduction in positioning error compared to the vanilla sliding window filter and the extended Kalman filter. So in summary, we show that it is possible to estimate a 3D relative position from only UWB and IMU sensors. Also, performance can be substantially improved using key points. And the proposed key point selection that we choose amongst many possible key point selection strategies can yield a 2 to 3-fold reduction in positioning error. And finally, pre-integration can reduce computation time as well as inter-agent communication requirements. And that's it for the presentation. Thank you. If you have any questions, feel free to read the paper or shoot me an email whenever.